Boston University, and he's going to talk about spatial Lagrangian fibrations in local IPL surface and mirror symmetries. So please, thank you.
First, I want to thank the organizers for the invitation. It's my pleasure to give this talk and the seminar. So today I want to talk about spatial Lagrangian fibrations in log labial surfaces and mirror symmetry. So I struggle a bit like when I hear that I'm going to give a talk in the algebraic geometry seminar. And so it might be a slightly different taste. Most of the talk will be, I will be sharing the idea of how to use the idea in algebraic geometry to do something else. And hopefully at the end, I can give you some results in algebraic geometry as a fun application. So the outline of the talk, I would first talk about the set of geometry, what I'm going to work on, and I'll explain what this SYZ fibration is, and I'll explain that on D'Abbezzo surfaces there will have some spatial Lagrangian fibrations, and I will explain what's their dual fibration, and I'll explain the idea of a proof. You know, there the Easter is already passed, but I'll give you some interesting, hopefully interesting applications. Oops. So the first player of the game are D'Abbezzo surfaces. So they're compact complex surface with MPO anticollinear divisors. And so from the classification of surfaces, so they're either P1 times P1, you can blow up a P2 at most 8 points. And so in total, you see that so the choice of D, there are 9 choices of, or P1 times P1, so there are in total 10 families of D'Abbezzo surfaces. And so in part, the degree of the D'Abbezzo surface is the square of the anticollinear divisor. And so, for example, that P2 is the D'Abbezzo surface of degree 9, because the anticollinear divisor of P2 is degree 3, and so by Bezout theorem we know that it's of degree 9. And so you can see that every time you blow up P2, it will decrease the degree by 1, and so so that you blow up at P2 at D points, then you get degree 9 minus D. And so by direct calculation, P1 times P1 has degree 8. So you can see that the degree will vary from 0 to 8. And when apparently it's wrong. So degree from 0 to 9. Degree from 1 to 9. And when degree is 8, there are 2 D'Abbezzo surface. One is P1 times P1, and the other one is the Hilsebrook surface F1. And so because that, so for the blow up P2, P2 definitely have a lot of smooth anticollinear divisor. They are smooth the curves. And so the broad P2 can inherit those smooth the curve as well. And so on P1 times P1, you can also construct a smooth anticollinear divisor. And by a junction formula, they're all elliptic curves. So this is one player of the game. And so the other player of the game are the rational surfaces. And so you always see that they're, in some sense, the mirror of the D'Abbezzo surfaces. And so rational surfaces, they're sort of self-manifest. They're a rational surface with an elliptic fibration, and they're minimal in the sense that there are no -1 curves sitting inside a fiber. And so any rational surface can be realized as broad of 9 points P2, which is a base point, of the pencil of the cubics. And so since it's the iterated broad P2, so you can compute its canonical bundle by the broad formula for canonical bundles, and so it's minus a fiber. And all the possible singular fibers are classified. So by Kodaira, and for the case of rational surfaces, are particularly classified by Pearson. And so there is a particular kind of fiber that I will be focused on today. It's called an ID fiber. So it's a wheel of P rational curves. And so it looks like, so they're D rational curves, and they form a cycle. So look like this. And so in total, there are D components, and then I will call it an ID fiber. And so each of them is a -2 rational curve. All right, so this is the, so the two main players of today. Oops. Oops, sorry. So these two things, I can view them as Calabi-Yau in some sense, in the following sense. So for each epixel surface, so, for the later on of the talk, I'll use the following set of notations. So Y is always means a dipexel surface, and D is always means a smooth anticanonical divisor. And by definition, since it's a smooth anticanonical divisor, and so I will call the complement X, which is this complement of D in Y. So there exists a holomorphic 2-0 form on X, which is actually meromorphic on Y with a simple pole along D. On the other hand, I'll use Y check to denote a rational surface. And so, so the notation with check, without check, will be related to the dipexel surface, and the notation with check will be related to rational surface. And D check is an ID, some ID fiber. And because earlier we said that its anticanonical divisor is minus a fiber, so there exists a holomorphic 2-0 form on the complement of this ID fiber. I call it X check. And this is actually a meromorphic 2 form on Y with a simple pole on D. And so usually with the pair, people consider the pair YD or Y check D check as this log Calabi-Yau pairs. But for me, I will assume something stronger. I really want the Ricci-flat metric. So unlike the compact case, so we know that given compact complex manifold with C1 equals 0, then by Yau theorem, there always exists a Ricci-flat metric in a given coded class. However, this is not that true, and this is in general not known for non-compact manifolds. And so Tian and Yao, they proved that if you start with actually a more general final manifold and smooth anticanonical divisor, and then on the complement, there exists a Ricci-flat metric. And it's a little bit weird because it's non-compact, and actually it will be an exact Ricci-flat metric. And in the sense that, so in particular, applying to this case, that Y is a dipexel surface and D is a smooth anticanonical divisor. then it's Ricci flat metric. That means that it's a closed 1-1 form. Actually, D closed 1-1 form. Actually, in this case, it will be exact and such that 2 omega squared equal to this this holomorphic Wellen form, which with its complex conjugate X. And so in the sense that I would say it's really a Calabi-Yau surface. So on the other side, on the rational surface side, so because that Tian and Yau theorem only applies to the case when this D is smooth, and so when D degenerate, the analysis become more complicated. But in the case of reference surface, it happens, one can really solve it, and it's solved by Heinz in the thesis. There actually exists a lot of Ricci flat metrics on this X check, depending on the killer class you want, and such that again, they satisfy the similar equation. This is the same complex Mongeon-Pei equation. And so with this Ricci flat metric, one can say that this both X and X check, they're hyperkiller because that the holonomic group, originally we know that it's SU2 because they're Calabi-Yau in the sense that because they exist Ricci flat metric. And so we know the holonomic force in SU2. And due to the fact that SP1 is the same as SU2, so they're also hyperkiller. So, so these are the actual content. So we're want to know what are the deformation space of log Calabi-Yau surfaces. And so McMullen, he studied the moduli space of pairs of a D'Apato surface with a smooth anti-cone divisor. He actually studied more general, like a rational surface with a smooth anti-cone divisor. So this moduli space is actually has a fibration structure over J line. So recall that we can have a forgetful map, forget the Y, and so you just forget the isosurface and send it to D. And so since D is under the curve, so it's parametrized by the J line. And so the fiber is, the fibers are in this form, which is the D perp is the elements in the Picard group of Y that's perpendicular to D via the standard intersection pairing, and quotient by some finite group. And so this is of dimension degree 10 minus D. And so, so this moduli space actually can be captured by the classical periods. So you consider the holomorphic 2-0 form on X, and you integrate the 2 cycle in X. So this is another description, which is useful in the later part of the talk. So on the rational resurface side, there exists the work of Gross, Hackenkill, and Friedman. They study the moduli space of rational surface with an ID fiber. And so this moduli space is similar. So this D check per is the elements in the Picard group of Y check, which is perpendicular to each component of D check. And so there's imposed by D relays here. And since Y check is originally has its brought up P2 at 9 points, and so it's H2, its Picard is rank 10, and then you impose D relation, so you get 10 minus D dimension. And again, a quotient about some Weyl group, which is finite group. And so with this presentation of the moduli space, so there's a very special points inside each of, so I should mention that there exist, so this ID for a rational surface, this D can also go from 0, which just means it's smooth, until 9. And so these are the possible families you can have. And so for each of the family, there exists very special points, because that I can send, so for each D, there exists an element which just send every element in D check per to just 1. And so that is the point I said, it's a distinguished complex structure with trivial periods. And this will play an important role and later on in the context of mirror symmetry. And again, that this is this moduli space can be interpreted as the classical period. So, and I learned it from this paper of Friedman. He explained that if you have any elements, any 2 cycle, which is perpendicular, any 2 cycle in Y check, which is perpendicular to every single component of E check, then you can always find a different, you can always homotopy to avoid the check. So it will become a 2 cycle completely false inside X. And so you can change this data to the period integral on this on the 2 cycle in X check. And so here that what I mean by normalized means so here that so recall that the fiber infinity is this ID fiber. And so the monodromy of this is 1E01 is conjugate to this. So this is the monodromy. Oops. It seems I have some problem with my pen. Okay, so sorry, I suddenly have some problem. Okay, and so there exists. You can, if you choose a loop, you choose a loop in the monodromy invariant cycle, which is like a vanishing cycle. It goes around the base, and so that gives you a torus. And you want to normalize this the period of this torus to be 1. All right. And so the upshot is that the period integral will completely determine if you know it's coming from either rational surface or the Paxos surface with this type of anti-cone divisor, then you will be able to capture its complex structure via the periods. And so it's similar to what we have for these surfaces. All right. Maybe I should stop for a second to see if there's any question. All right. So now we're going to explain the goal I'm trying to work on. So the Strominger-Zaslow conjecture, it predicts that Calabi-Yau manifold would emit spatial Lagrangian torus vibration near large complex structure limits, which is I'll skip that. And so what they mean by special Lagrangian is that it's a half-dimensional submanifold in the Calabi-Yau manifolds, such that the Ricci flat metric restricted on it is strictly 0, and the imaginary part of the holomorphic volume form restricted on L equal to 0 as well. And so if you have this condition, this is what we call the Lagrangian. And if you have furthermore this condition, then we call it special Lagrangian. And so why is this important? Because that so Calabi-Yau manifolds in various aspects, there's people who want to understand. And from the mirror symmetry point of view, so this spatial Lagrangian fibration structures that give you some idea of the geometric structure of Calabi-Yau manifolds. And more than that, tells you how to construct the mirror of Calabi-Yau. It's just by dualizing the torus vibration you have. And so this gives you an explicit recipe for constructing mirror. However, that original conjecture doesn't say explicitly how to deal with the singular fibers. And in the case of the Betzel surface and rational surface cases that I'm going to talk about today was also conjecture, in particular conjecture by Denis Auroux. It's about around 10 years ago. So now I'm going to explain the, so maybe I should say that, so what are the examples of spatial Lagrangian vibrations? So far, there are two examples known. So one is like if you have a torus, and then because the Ricci flat metric is simply flat, and so we all know how to write down the spatial Lagrangian vibrations. And the other one is K-free surfaces, which I will say more later. So K-free surfaces, they're also hyperkähler, and so one can use hyperkähler rotation to govern elliptic K-free surfaces to spatial Lagrangian vibrations. And these are the two examples that we know so far since this conjecture in '96. And so this is the result with Tristan Collins and Adam Jacob. So we have the, so the result is follows. So if you start with the Betzel surface or surface, and take a smooth anti-cone divisor, and then the complement will admit the spatial Lagrangian vibration. And what's a section? With respect to the Tian metric that I mentioned earlier, which is an exact Ricci flat metric. And so this solves this conjecture of SYZ or Auroux. And so in particular, in the case of P2, there are 3 nodal singular fibers. In the case of rational surface with smooth anti-cone divisor, there will be 12. Generically, there will be 12 singular fibers. And so for people who work in mirror symmetry, that the statement probably might touch your nerve, because that so recall that the mirror of P2 is a superpotential. Is x plus y plus 1 over xy. And so this is from C2, C star square, to C. And so this guy has 3 singular fibers. And so that's sort of so you probably sort of smell a sense of some mirror symmetry is going on here. And so, so more than that, so if I that check to be some hypercare rotation of X, so what I mean is that I changed the, so recall that originally I have this capital omega and little omega, which is a 10-year metric. So now I'm going to change, I will just keep the same underlying space of X, but with a different scalar form. I will just use this, the real part of capital omega, the holomorphic volume form, as my new scalar form. And I will use this combination of two forms as my new holomorphic volume form. And that will give me a new complex structure on X, on this underlying space of X, which I'll call the X check. And so this is this procedure is called hypercare rotation. And the key point is that if you have a spatial Lagrangian in X, then after hypercare rotation, it becomes holomorphic curves in X check. And so the theorem is that this X check is compatified to a rational surface Y check. And so that's the reason why I use this notation. And by adding an I fiber infinity, D is, so here D is the degree of the de Pazzo surface of Y. And so, so now the symmetry is coming more, seems more related, because that in the work of Oruka-Tsakov, Olov, they proved that if you want, on one side, one consider the de Pazzo surface, and they consider the derived category of current sheet on de Pazzo surfaces. On the other side, they write down the mirror superpotential, and they consider something called Fukaya-Saito category. So this guy is a function from C star square to C, and so, oops. So one can fiber-wise compactify this map. Oops. And then one can add the oops, why can I change it? One can change fiber-wise compactify this map, and then one can add an ID fiber infinity. And that will give you, and that will, they prove that this gadget is actually topologically is the rational surface. And so that's make it more like a statement of mirror symmetry, because that from the example, let's say in P2, you see that actually that will really give you the mirror. And actually this correspondence respects the deformation families. So recall that there's 10 families of de Pazzo surface, and there are 10 families of rational surface with an ID fiber. And so there will be one-to-one correspondence, because that when I do hypercare rotation, the degree of the de Pazzo surface corresponding to this, the D of this ID fiber. And so in the case of degree 8, you get two families of de Pazzo surface, which is F1 and P1 times P1. And on the other side, from the result of Ricard of Orlov, you can compactify to of the mirror potential of P1 times P1 or Hilbert surface F1. And this hypercare rotation will preserve the family. To give you some smell of mirror symmetry is really going on. So the second result is saying that so because that the mirror symmetry is mostly steady for in the case of local IBL surface is when D is maximally degenerate in the sense that as degenerate into wheel of rational curves. And it's particularly studied intensely by Gross and Keel. And so in the rational surface, we also prove a similar result. And so if you have a rational surface with an ID fiber, complement will have a spatial Lagrangian vibration. And moreover, you can do a hypercare rotation, and after hypercare rotation, you can also compactify to another rational surface by adding an ID fiber. And so then a natural question to ask is that if the spatial Lagrangian vibration in these two theorems, they're really dual vibration of each other. Okay, so these are the first statements that I want to talk about today. So to stop to see if there's any questions. Okay. Right. So the first idea to understand this question is a toy model is K-thesis. As I said, these are the examples that we know the spatial Lagrangian vibration exist. And so first, there's a standard fact that's given a K-thesis surface. And if there exists a smooth Lilith curve, or I think in general, more generally, if you have a arithmetic genus 1 curve, then X will be an elliptic surface. And so then one can have the following game. So we start with, if I start with a K3 surface, I want to say it has a spatial Lagrangian vibration. All I need to do, if it has a spatial Lagrangian, that means that after hypercare rotation, it becomes an elliptic vibration, because the hypercare rotation will send the spatial Lagrangians to holomorphic curves. And if I have a spatial Lagrangian tori, they'll become elliptic curves. And so I just need to say that the K3 surface after hypercare rotation will contain at least one smooth elliptic curve. Then we know from the standard theorem that we know that there exists an elliptic vibration on the K3 surface after hypercare rotation. Then we can hypercare rotation back. They give you a Lagrangian vibrations. So actually, so with 1-1 and Luca, so we proved. I think this is probably something well-known, but I didn't see it in the literature, and so we actually so every algebraic 3 admits a spatial Lagrangian vibration. We actually prove a stronger statement, but this is like a spatial case. So, and moreover, so to argue that the K3 surface and it has an elliptic curve, all one has to do is you can just check that there exists a isotropic class which falls inside the pickup group, and so then the Riemann-Roch theorem will help you to then smooth the curve, and so that makes the case of K3 surface very simple. And so if we want to deal with the non-compact case, so there's a few difficulties. So after hypercurve rotation in general, the geometry can be very transcendental. Usually we start with something we know, some geometry we know. After we do hypercurve rotation, we lose control of it. And the second thing is that since this is non-compact, we don't have Riemann-Roch anymore. And so we need to produce a smooth curve. And so in the K3 surface, if we have a divisor, we can talk about linear system. And so the question is, how do we get, if we have a smooth curve, how do we get a fibration structure? And so these are the difficulties. So the schedule proof, and so sorry that now I won't be able to avoid analysis, and so let me brief explain the idea of it. And so if we start with a Lagrangian, that means that the kilophone, the receive-flat matrix read-on equal to 0. One can restrict the holomorphic N0 phone on L, and then it will be the volume phone of L up to some phase. And L is a special Lagrangian when theta is a constant. So Calabi-Yau case, the main curvature is given by the J, which is the almost complex structure. In here that we're using the standard complex structure, times the grade acting on the gradient of theta. And so, and one can consider something called mean curvature flow by deforming the Lagrangian in the direction of mean curvature flow. And the reason why we care about this is that if one can prove that the flow is convergent, then that means the left-hand side is 0. That means the mean curvature flow on the limit will be 0. And in the case that the mean curvature is 0, that means the gradient of theta is 0. And that means that you end up with spatial Lagrangian. And so, this is the hope. But in general, this is a hard question. Very few examples you can prove that the flow can really converge. And actually, most of the time, one actually would expect flow will not converge in most of the cases. And so the idea is that we construct a almost spatial Lagrangian tori. And we prove that in this case that the mean curve flow really actually converge. And this is this occupies a huge part of the work. Maybe I would just say this. Probably that's a totally different DG seminar talk. So the second step. So now I can do hypercurve rotation to X check. And then the hypercurve rotation will move this spatial Lagrangian tori to a smooth curve. And so then I will replace the analysis part of the Riemann-Roch to something which I change it to Lagrangian mean curve flow. And then I'll get a smooth curve. And then the question is how I need a replacement of the concept of linear system in algebraic geometry. And so it's in general hard to deform a submanifold. While that in algebraic geometry, the people has another notion, which is the concept of stable maps, which is so in symplectic geometry there is a similar notion. It's called the theory of the J holomorphic curve. And so the idea is that we do not deform this smooth of the curve as in some manifold inside X check. Instead, we deform it as this J holomorphic curves. And so when it is smooth, the work of Vasson and MacLean, that the deformation of holomorphic Lagrangian, in this case, this deformation, the smooth elliptic curve, is unobstructed. So near a smooth elliptic curve, the deformation is nice. However, that it will always deform to some singular one, which is not avoidable. And so now we have, we're looking for elliptic curve, like the stable maps into X-check, which is a non-compact complex manifold. So compactness will be an issue. And so here that, so in simplex geometry, there's a standard theorem called Sykes-Willenbeck-Gromov compactness, which is you can view it as analogous of a stable map compactification. However, that here actually difficult again lies in analysis that the geometry is actually very degenerate, and so the standard theorem does not apply, and so we have to prove a stronger version of compactness theorem to deal with this. And so, so what we prove is that we have a sequence of holomorphic curves as passing through a compact set, a fixed compact set, then it cannot escape to infinity. And so that will help you to say that the deformation of this starting elliptic curve is closed. And so if I want to say it give me a vibration structure, all I have to do is to say that the deformation is open. And so from the theory of J holomorphic curves, that from the compactness theorem, that we'll be able to tell what kind of bubbling can occur. And so the analysis will be very similar to what Caldera did when he studied the classification of singular fibers for minimal elliptic fiber. And then we can, with more analysis, we'll be able to prove that the deformation is open. And so that gives you a vibration structure. And so if one cares about just simply the vibration, that's it. But this vibration is actually, X-check is not clear what X is. And so here comes the next step. So with this, this X is actually, say for example, the complement of a smooth n-angle divisor and the passive surface. This is either simply connected, or this pi 1 has only torsion. And so you can use that to deduce that the base is actually simply connected. And then this is the first time I really appreciate this uniformization theorem, because that tells me that this base B is actually C or D2 or a disk. Then the non-compact manifolds. So there's a theorem of Yao that tells you the non-compact manifolds with a complete and metric, and which such that the Ricci curvature is non-negative, then it cannot has any non-constant harmonic functions. But then D2, the disk, has a lot of bounded harmonic functions. You can use the vibration structure to put it back to X-check, while X-check is Ricci flat. And so we can apply Yao theorem to exclude this case. And so B is just C. With this, then algebraic geometry can come into play, because that using analysis, we construct local sections of this vibration. So a priori, this is not necessary, actually not really a elliptic vibration yet. It's a genus 1 vibration, because that's X-check is actually a priori very transcendental. We construct some local vibrations using monodromy. So you can map this neighborhood of infinity of C to as M11 bar. And you pull back universal family, because we can have a control of monodromy that will give you a complexification of X check by adding an ID fiber at infinity. And so we get a complex surface Y check. And to see what this Y check is, so by classification of surfaces, it's not minimal. So we just exclude one by one in the list. And so that means it has some -1 curve. And so using the canonical bundle formula for the surfaces, there will be this -1 curve will be sections. And so once it has a section, then you know it's algebraic. And then using this Castelnuovo's rationality theorem, you can deduce that as Y check is really a rational surface, is rational, and so as a rational surface. And so, so this part, I actually don't know the corresponding thing that's in analysis, which seems not avoidable for the conjecture at the moment. All right. So with this, the existence of vibrations. So earlier that said that on one side, one can have on the complex, on the de Pezzo surface, one has this spatial Lagrangian vibrations. On the rational surface, one has also another spatial Lagrangian vibrations. One can ask if they're mirror or not. So with, again, with Tristan Collins and Adam Jacob. So one are with the complex moduli space of the pair of the Pezzo surface with the smooth anticone divisor, which is this moduli space is stated by McMullen earlier. And on the other side, one consider the rotating surface. So recall that if I consider the Pezzo surface of degree D, it's mirror, one expect that it's mirror to a rational surface with an ID fiber. And so, and by the Torelli theorem, there exist distinguished elements in the deformation family. And so I will fix that particular distinguished complex structure, and then I'll consider its scalar moduli. And then one can has, so one choose a section, and then one write on a very explicit mirror map. And under this mirror map, so the spatial Lagrangian vibration that constructed in the previous theorems, they're actually indeed dual to each other in the sense that the complex and symplectic fine structure exchanges, and the volume of fibers are inverse to each other. So here that actually there are some extra parameters in the scalar moduli, which I don't know how to see that in algebraic geometry actually. There's a weird one additional parameters here. And so originally that this scalar moduli in some sense is one dimension larger than that. And so one actually need to specify this this alpha here, which is sort of mirror to, so recall that the complex moduli of this pair of YD has a vibration structure to J line. And so this tau is the modulus of the smooth of the curve that I choose in this in the economical system of the de Pezzo surface. And so recall that, so this imaginary part of tau will measure how this elliptic curve is degenerate, is closer, how this smooth of the curve is is approaching the nodal elliptic curve. And so that the corresponding thing, this alpha here, measure that on the other side, how this vibration collapsing. And so this parameter doesn't, I don't know how to explain in algebraic geometry in a better way, but that is mirror to how this the curve degenerating into nodal curve. Right. So I'll maybe step to see if there's any questions. Right. So yes. Okay. So it's put a few remarks. So this mirror map is actually not new. So this mirror map appears in the work of Grosson. We modify it because one don't see this alpha parameters here, and actually also there's a similar work of Hack and Keating. They proved the homological mirror symmetry, and they also use distinguished complex structure in the deformation family as the mirror of the when the Fukasido category is equivalent with exact symplectic form, while here that we're using the TL metric, which is an exact form. And so one sees some echoes in the literature. And actually the whole thing, this whole theorem actually coming from how to define this scalar moduli actually. And because that's in analysis, usually one is done for Ricci flat metric, but here that in this rational surface, we can actually construct a priori tons of Ricci flat metrics, and so we actually prove the unique for Ricci flat metric on the rational surfaces. And then assuming this, then this mirror symmetry is actually coming from a direct consequence of the toric theorem. So recall that so on for the Petzl surface, for the rational surface with an ID fiber, there's a toric theorem of Gross, Hack, and Kiel. You can pinch down the complex structure by looking at the periods. And so, so here that so one start with this spatial Lagrangian vibrations in deep here, and we do a hypercare rotation to a rational surface with an ID fiber, and then using a toric theorem, you can prove that this the resulting hypercare rotation is actually biholomorphic. And so, in other words, that the mirror map is actually composition of hypercare rotation. But this two hypercare rotation actually does not fall on the same twistor line. So in old days, that in the beginning of this development of mirror symmetry, people are guessing that mirror symmetry is hypercare rotation, but then people realized, oh, that's not the case. But actually, still mirror symmetry is related to hypercare rotation, but actually they're related by a composition of two hypercare rotation, but not just one. And so there's some, sorry, when should I?
Still have 5 minutes.
Okay. So there are some applications to enumerated geometry, and so so with Zhonglu Li and Xiuchang Liao, we computed in the case of this how the space of the vibration look like, and or how this to deduce some statements like if you count the open Gromov-Witten invariant like in P2, it will be exactly the log Gromov-Witten invariance with maximal tangency in P2. So you recall that if you have a smooth curve, and you can count the number of rational curve of degree with maximal tangency only touch the smoothly curve at one single point. And this can be captured by counting open Gromov-Witten invariants with fibers on this spatial Lagrangian fibration. Maybe we'll jump to the application. Maybe most of talk is not that algebraic. So I'll give you a theorem in algebraic geometry probably, although it's a very classical result. I even don't know when it's known, but I believe it's known maybe in 18 something. So it says that given a smooth curve inside P2, you can always find in Z3 times Z3 inside automorphism P2, and that's preserved this smooth curve. So this is a probably quite standard result, but I'm going to give you a 100-page proof of it. So idea follows. I will start with, so on the complement of this smoothly curve, I'll call X. One can do a hypercurve rotation. So there exists a spatial Lagrangian fibration. And then we do a hypercurve rotation, we get X check. And then we know that the X check can be compactified to rational surface. And the key point is that this hyperrotation is different from most of the cases because we actually will be able to know what this hypercurve rotation is. And so because that we know this is a rational surface and it has an I9 fiber. And actually there's exactly one, and then that's an extremal one. And so this one can be written very explicitly. And so with more analysis, we that the 2-0 form from hypercurve rotation on X check is actually not just a holomorphic 2-0 form on X check, but when we extend to Y check, it's actually neuromorphic. And so then this thinks that this extremal rational surface you can write it very explicitly. Then there exists Z3 times Z3 inside the automorphism group. And that's preserving omega, the 2-0 form, that's easy. Then we proved some uniqueness theorem, that's where the hard analysis is hiding, that this scalar form is also preserved. But then altogether, you can, when you do hypercurve rotation back to X, then this automorphism actually something fixing capital omega without check and little omega without check. And then we prove that actually extends to over the original smoothly curve, because this map's originally only defined on the complement of the curve, but one can prove that it extends actually. And so then with all this analysis, finally I can give you an algebraic geometry statement, although it's quite standard, but I think it's, I view it as an interesting application. Maybe I will stop here. Thank you.
Okay, thank you very much for the talk. So any questions, comments? So I'm kind of curious that do you think is it possible to construct higher dimensional examples?
I think it's pretty hard. So I think that the progress of SYZ has stopped for a long time with the original conjecture, but Yan Li has a very amazing work recently. He constructed spatial Lagrangians, say on the complement of the, okay, so construct for Fermat hypersurfaces, you construct the spatial Lagrangian vibrations on a huge part of the, on the Fermat hypersurfaces, but that doesn't include the singular fibers. So this is like a trade-off. So here we are to advantage a lot of things in four-dimensional, while that will have a full vibration and a full SYZ conjecture, while that Yanli can do for all dimension, but it would there's no control of singular fibers.
Uh-huh. Okay, any other questions? Okay, so if not the case, let's thank the speaker again. Yeah, thank you very much.